Our project aims to employ computer vision techniques to identify contraband items in X-rays of vehicles crossing the U.S. border. By automating the detection process, we seek to protect the citizens by reducing the number of illicit goods entering the country.
We accomplished this task by finding ways to compare different X-ray images of vehicles. This involves many challenges. First of all, different scans are at different resolutions, so there is no direct way to compare them. To fix this, we use something called a variational autoencoder. In its simplest form, a VAE takes images, compresses them into vectors, and then turns those vectors back to images. By making the size of the compressed vectors smaller than the original image shape, the VAE learns to efficiently compress the information in the image into what we call a latent representation of the image. Unfortunately, our vectors were created from images of different shapes, so they are different lengths. In order to compare the vectors of the two images, we introduce reduction operations that take arbitrary size vectors and transform them to be a fixed size.
Now that we're able to compare these images, we move on to the next stage of our research, vector databases. In this part of our research, we explore efficient and scalable distance metrics between vectors. Because millions of trucks cross the border every single day, we need an efficient way to store vectors as well as an efficient way to retrieve them. After researching a lot of different methods, we settled on a concept called hierarchical navigable small worlds.
Hierarchical navigable small worlds refers to a way of organizing networks where nodes are grouped into clusters, which are then connected in a hierarchical structure. This arrangement allows for efficient navigation between nodes. Within clusters, connections are dense, enabling quick local exploration, while connections between clusters provide shortcuts for long-distance navigation. Essentially, it's like organizing a large library into sections and subsections, making it easier to find books quickly both within sections and when moving between different sections. We found that our implementation was extremely efficient and was able to find the nearest neighbors to a vector from a database of millions of vectors in only milliseconds.
Finally, we're currently working on the decision logic for whether or not a vehicle gets flagged for contraband. This is a very abstract problem that we are currently exploring, but we plan on comparing sets of nearest neighbors of vectors to flag certain statistical outliers that may be likely to have contraband. It goes without saying that the security of our borders is extremely important. Unregulated contraband that makes it through the borders harms our citizens. As a result, we expect our research to have a very positive impact on our society. Thank you.